So thank you for inviting me here. It's always great to come here. So Partha asked me to give a sort of, I don't know, maybe a sociological talk, right? Which is, as you just heard, I spent time at Bell Labs. A number of my Bell Labs colleagues are here. And actually, I will say one of the interesting things about coming back to the world of neuroscience, which I've only re-entered very recently, is to discover that there are some old friends in it. So that community of thinkers who at that time were kind of mostly postdocs, working in the undergrowth, now seem to be running the field. And so one of the questions is, why Bell Labs? And of course, anybody who was ever at Bell Labs spends the rest of their career trying to reinvent it, and I think that's a mistake. But so I wanted to say a few things about why that worked. So Bell Labs was the phone company. So let me just give you an example of something that was driven by a phone company problem. And there are a bunch of folks there, some of whom you will recognize. Certainly my Bell Labs colleagues will recognize them. Horst with his long hair around an MBE machine. And so this is a machine for growing solids a single atom at a time. To make perfect solids by laying down atom after atom after atom, layer by layer, so that you could program a semiconductor. It's kind of a bold goal, rather hard goal to imagine you can make a solid by putting every atom in exactly the proper place that you want it to be. It's kind of a lunatic goal. Why would you even want to do this? Well, there was an obvious reason to want to do this, because this was the phone company. The phone company depends on electronics. You wanted electronics to go faster and faster, so you need to have better transistors. The transistors had to switch faster. The reason they wouldn't do that is that there are impurities in the growth, so you want to get the impurities out of the way and put all of the atoms in the same place. Very, very clear corporate motivation. I mean, Bell Labs was not doing science because it cared about science. Of course, it did care about science. It was doing science because it could see the things going on. Now, so what do you discover when you do this? Well, yeah, they sort of made better transistors, right? But they also discovered the fractional quantum Hall effect. And this is, as we know now, a fundamental property of topology of two-dimensional electron gases in very high magnetic fields. What you're seeing there is discovery that actually particles don't just come in fermions and bosons, but you can actually have particles with fractional statistics and fractional charge, all made up out of electrons. Nobody went after this problem because they were interested in the fundamental physics of two-dimensional electron gases. It wasn't that there was a science motivation that says, we want to understand what happens to 2D electron gases in large magnetic fields. Well, there are a few people who cared about that, but not enough of them to be able to spend a 10-year experimental effort to build something. The other thing about this is what you know is that, by the way, that this discovery becomes absolutely inexorable the moment you build those devices. So if you ask Horst Sturmer, the guy who's sitting here, what his most important contribution to science is, he would not say, in fact he does not say, that it was the discovery of the fractional quantum Hall effect. He said it was the invention of modulation doping that made this possible, because that was an important engineering invention. And after this, somebody was going to discover the fractional quantum Hall effect. It was just straightforward. It was sort of sitting there. Now, by the way, question of why did Bell Labs care about neuroscience? Well, actually, there's a huge overarching business driver for Bell Labs to compare, because it's in the communications business. Partha already mentioned, you're going from telephones, you need to understand what bandwidth, you had to do a lot of psychophysics, people were interested in automatic speech recognition, you get to human perception, pretty soon you get to the question saying, well, I wonder how the brain does this. And remember that some of the very early research projects actually at Bell Labs, going back to when it was in Manhattan in the 1940s, was research in microphones. And I'm told actually that they were collecting coal from various places around the world, because some, for acoustic microphones, some coal made better microphones than others, and they wanted to understand why. And They were really coal bunkers in there. But of course, they worked on hearing aids, video phones, and then eventually fMRI as part of that. Now, the other thing to remember, however, is that when it comes to neuroscience, there was sort of an inbuilt competitive advantage because as a result, there are already people worrying about, as Partha described, engineering problems. So people already working on hidden Markov models for speech recognition. The ideas of neural nets were already there. NMR, of course, as a science technology, was widely used in science, and everybody knew how that worked, but also things like human factors analysis, psychophysics, all of those things. And partly because Bell came to these problems with a different mindset from everybody else. And then there's a kind of a methodology which I think we should well adopt. Is the first thing is you try and find a really hard, important problem that's going to take you a long time, and you do it really well. That's very counter the modern academic culture, which is sort of publish and get out quickly. And we need to devote resources to those things because, and I know when I get a research grant, you do the easy things first, and then the hard things get kind of pushed later and later. And instead what you should be doing is you should be saying, well, what are the really hard things that I have to do? That's how engineers approach projects. I'll do those first, and if that doesn't work, I'll go do something else. So, note about Argonne, actually. So, I'm at Argonne, actually been working on low-carbon energy since 1946. The history of Argonne is that it came out of the Manhattan Project. In Chicago, Fermi and his collaborators in 1942 made the first controlled nuclear chain reaction. After the war, Argonne was founded to commercialize nuclear power for peaceful uses. Now it's kind of a big place. We have 3,500 people, spend $750 million of the US federal government's money every year. And a lot of the things that we do have kind of an outgrowth of that, but particularly in terms of, still very much in energy technologies. Energy technologies for us these days maybe batteries or things like this. So then one question should be, well, remember that when I talked about Bell, I said, well, there was a business driver, there was a business advantage, and then there was a methodology. Argonne isn't this, but why should the Department of Energy care about neuroscience? Well, not because it cares much about brains particularly, but current computing at 10 to the minus 14 joules per bit, which is kind of the benchmark thing that we do, is simply unsustainable. The cloud is not virtual, the cloud is real, the cloud is melting the permafrost right now. It's running at about 6 to 10% of IT, is about 6 to 10% of energy consumption on the planet. It's growing, of course, very rapidly. If Moore's law were to continue in operation, which thank God it won't, by the year 2040, you would simply project that the whole of global energy consumption would be used for IT. So that ain't going to happen. On another scale, one of the things that Argonne does is that we do very large-scale high-performance computing. We're about to put in a 200 petaflop computer. And we don't just buy these things, we design them. We're designing the architectures, and we're now working on exascale. And an exascale 10 to the 18th floating point operations by the early 20s is going to be about 25 megawatts. That is the last computer of that scale that one will build in that kind of architecture in that way. It's heating, right? No, but so now the answer is, why is it so? By the way, what's wrong with this number? Physicists in the audience know that there's a Landau limit, and that's kT times log of something, which is always 1 per bit. So you've got 6 orders of magnitude, provided you want to carry on operating at room temperature. Right? So there's 6 orders of magnitude to be gained anyway. And by the way, why is it heating? It's heating is because of the architecture is nuts. Current semiconductors have about 14 layers of metallization to connect the power source, which is on the outside, to the processor, which is right in the middle, and that's the heating. That's why processor scaling stopped at the gigahertz scale about a decade ago, and we now go to multiple scale parallelism. And by the way, our exascale computation, if you want to get exascale power out of it, you're going to have to be able to code in a way that there are a billion parallel operations being done on the machine. That gets increasingly hard as one goes through these. And actually, as you move from one scale of high-performance computing to the next one up, typically there are fewer and fewer algorithms that work. So the classes of problems that you're able to solve on these big machines actually get smaller, not bigger. You don't get more out of them. You can often get less. There are problems that don't work. So, the other driver for us is, as I mentioned, we support large-scale science facilities. We like really hard problems because they test and they drive the things that you want to do. Computing is one, imaging is another one. Okay? So, from my perspective, what's our competitive advantage, and the nice thing about that is I think it's also yours, is that we in the DOE system as a whole host these big science infrastructure facilities that you can't get anywhere else. So we have a synchrotron X-ray source. This actually has 7,500 users a year. Interestingly, only recently did we, and actually I think it's me, have the idea that we should be using this for brain mapping. And it's kind of interesting because it sort of works. And we're getting to the stage where we can do brain maps, obviously dead stained brains at micron scale resolution. I have a whole mouse brain now done that way recently. And it took about a week to take the data and about 6 months to do the data analysis, something which is very familiar to you. This thing is about to get 6 orders of magnitude brighter. That means, we have more photons. We can take more data. What we do with it, I don't know. And on the other side of this, of course, we have these large-scale computing that we're interested in. But another point I will say, and this comes to Partha's point about engineering, is we are actually an engineering lab, and the engineering of the energy problem is all about networks these days. So we have folks with a lot of expertise. The hidden Markov modelers at Argonne are, for example, people doing agent-based modeling to understand how things work. And if you really want to be modeling neuroscience, agent-based modeling takes people and turns them into agents. But we have models of cities with people running around, behaving like people. And it turns out you can use them to do science, surprisingly. One of the discoveries that some of my colleagues made was actually about disease transmission by MRSA. I was taught a few years ago that MRSA was a hospital-acquired infection. That the way to get rid of MRSA, so this is methicillin-resistant staphylococcus, which you can die from because it's hard to cure, and it was sort of believed to be resident in hospital environments, and so the thing to do was you locked down the hospital, you fumigated it, you killed everything. It turns out that actually if you analyze data about this and look at it sensibly, it's now a community-based infection. It may once have been a hospital-based infection. There are lots of carriers. About 10% of people in this room carry MRSA. You'll all be healthy, but look around at your neighbors and wonder about this. Very few people get seriously sick with it. And you discover this from epidemiology. And this goes back, of course, to how John Snow in 19th century London discovered that cholera was a water-based disease by going and looking at the people who got cholera and which well they got the water from. That was the database in which to do this. So there's so if you come with a kind of engineering and systems-based bent to these things, you look at problems in different ways. Will it be useful for neuroscience? Frankly, I don't know. But I think it's one of the strengths of bringing many disciplines together that you get people who, in the same way as the Bell Labs, is that people were just thinking different because they had different classes of problems that they cared about. And they came with a different set of baggage than the community that they worked with. So, our perspective is, Connectomes is a useful problem to start with. As you know, it's sort of about 100 billion neurons, 100 trillion synapses. And by the way, since a synapse, if you want to find a synapse, you need something which can measure down on the 10 nanometer scale, which is typically electron microscopy. And brains are 10 centimeters across. So if you want an imaging technique which is going to do 3D, Google brain maps. So that's a zettabyte of data. We've been talking about petabytes. Now, a zettabyte of data is now currently about the global internet traffic. Okay? So it's a big number, but it's not an absolutely impossible number. If you think forward 10 years, maybe a zettabyte won't feel that big. I'm not saying, of course, that you need a zettabyte of data to actually understand the whole of the connectivity of these things, but you may have to take a zettabyte of data. Now, the other interesting thing is that we can now take a zettabyte of data. So the beam power that we have with the next generation of X-ray synchrotrons will allow us to connect 10 to the 21 photons. I don't quite know what we will do with that. We obviously have to go into the mode of particle physicists and astronomers where you can't analyze that amount of data. You start by throwing a lot of it away. And you, of course, have machine learning methods to understand exactly what the data means. But there's a way to do that. So I think I'm getting in the way of a snack. But as I say, I've got a kind of odd perspective on this and coming about this from very, very different directions. I totally support the point of view that engineering will drive this. We were discussing at breakfast, I think, the earliest stages where we will want to be using what I think of as real neuromorphic hardware will be edge computing. Because, I'm actually handing my phone. I want to ask you a question. What is this? It's a phone, right? Well, actually it's not. It's mostly a battery. Right? Most of the thing which is in here is a battery. Most of the thing which is in this is the battery. Most of you spend your lives wandering around looking for somewhere to plug something in to get electrons to feed it in. Right? And of course, the problem that while we tend to talk about architectures for neuroscience, one of the other things that the brain does is it provides the power source at the same point where the computation is being done. And that's a very important piece of the architecture, and that's what is killing CMOS. What is killing CMOS is that the thing that thinks, which is really tiny in here, is powered by this enormous battery pumping in power down wires all of the way to the scale where you can do this, and that's a really dumb piece of hardware. So some kind of next generation hardware will combine electrochemistry and electronics. There's a very large piece of Argonne that does research on next generation battery technologies, which involves designing materials at the scale where the electrochemistry happens. And there's a whole science project associated with combining electrochemistry and electronics within novel materials, which is entirely independent of architectures and is really about next generation hardware. And that eventually has to come. So I'll stop. Yeah, that's right. Or maybe it's kind of the same thing. You distribute, you would distribute that, you want to feed it, right? So and by the way, I can physically imagine hardware that can do this. There are plenty of materials where ions move around. As I say, the whole of a battery, if we want to understand how a battery works, although it's kind of again, 18th century technology, to understand that it's really motion of ions on the nanoscale and maintaining potentials, in the same way that the brain does actively. And there's no reason I shouldn't combine that with, computation on that scale. So I say that my version of neuromorphic isn't just an algorithm or reprogramming a bit of CMOS to put in long-range connections so that it kind of works more efficiently. In the end, I think we have to have entirely different hardware technologies. And I don't kind of know what they will look like, but I think it would be fun to start trying to build them, think about how you would make them, and of course people are. And those kind of problems are kind of the grand scale engineering problems, which I think can help neuroscience one way or the other. Stop and let you get started. Thanks.